in the ex vivo model. So then the cell, we have treated the rhodamine fortified this nano formulation. We could see the cells are nicely uptaken these nanoparticles. And after that, we have developed the diabetic retinopathy model using the retinal epithelial cells, and we have used as a high glucose, we have used as a, to introduce that model, and we have monitored the caspase-3 as a caspase-3 and the VGF, because those are the apoptosis and the angiogenesis is the challenge in this model. So we have developed that one, and after developing this model, we could see that when we challenged first with the high glucose and then treated with this nanoformulation, they are preventing this level, VGF and the caspase-3 here. They are also reducing the reactive oxygen species in the intercellular level, and also the high glucose induce the cell death or mitochondrial damage is prevented by this nanotherapy. They are also, this nanoformulation also reducing the apoptosis introduced by the high glucose. Then we have done the biodistribution. We could see they are located in the brain, and also they are accumulated into the liver and the kidney. They are mostly the highly metabolic organ and may be attributed due to the excretion of this nanoparticle. They are highly safe. There is no changes in the histology. So pharmacokinetic study we have done, and where we can see they are increasing the median resident time of this melatonin maybe 20 times. So from 1.6 hour, the bulk one, to 26 hours. So due to this nanoformulation. And then we have used the streptozotocin. This is a very standard model for the diabetic retinopathy. So the blood glucose level, that body weight alteration by the streptozotocin is returned to after the therapy. And we could see the open field behavioral study, the cognitive impairment, and they become normal, almost normal after the treatment. Then we have done the retinal section where we could see the streptozotocin group showing the swollen ganglion cell death in that particular STZ, which was prevented in the therapeutic group. So, and we also see the flattened that thickness of the streptozotocin is also become compacted following the therapy. So then we have done the NG2, which is a marker of the retinal it is a marker of the pericytes that is residing into the molar cell layers of the retina. So that is completely gone or inhibited following the STZ treatment, and they came back after the therapy. And also we monitored the CD31 as a blood vessel marker. So we could see they are highly enlightened, means stimulated following the STZ, which is also returned to the normal following the therapy. That is the next slide. Next panel is for INOS. That is a very well known, like the means like the anti-inflammatory marker. So that is lightened up following the STZ therapy and diminished following the nanoformulation group. So finally, we have checked the involvement of the VGF and caspase-3 here. So you can see the VGF is highly stimulated following the STZ therapy, which was become control or almost level of the control following the therapy, and that is supported by the Western blot. So you can see the caspase-3 activation and following the STZ, and also there is a VGF upregulation, pixel delta upregulation, which are inhibited following this therapy. The last panel of the Western blot. So we have presented them in the graph. Bar diagram here. So they are significantly controlling this pathway for executing this kind of efficacy. So we can conclude like this nanoformulation is showing the anti-diabetic, anti-retinopathic activity in both in vitro and in vivo model. So through the inhibition of caspases VGF dependent pathway. So Last slide is the acknowledgement. I'd like to thank my director, my collaborator, Dr. Roy Chaudhary and Professor Sharma here. So he helped us a lot. Thank you, Professor Sharma, and the funding agency, and lastly, my hardworking students. So these are the students mostly involved with this project. So thank you very much for your kind attention. I'd like to take some questions.
Thank you, Dr. Surajit. Actually, we can have one quick question because after that we have to start another session. Any question, please? Okay, there's no question. Thank you very much, Surajit. Now I invite all the speakers on the dais. Please come so that we can felicitate.
Thank you all the speakers for your wonderful presentations. Okay, let us continue with another session. It is one of the emerging area on the pharmacogenomics and precision medicine. So without wasting much time, I would like to invite Professor K.B. Tiku. He is HOD of the Department of Pharmacology and Toxicology in S.A.S. Nagar as a chairperson. And Dr. Abhay Sangamwar is a co-chairman of this session. Associate Professor working in the Department of Pharmaceutics. Please come on the dais and do the needful. Thank you.
Now we are heading towards the next session about the session 11, Pharmacogenomics and Precision Medicine, with the first speaker, Dr. Veera Suvarna. Dr. Veera Suvarna holds MD in Pharmacology from Grant Medical College and Sir J.J. Group of Hospitals, Mumbai. He also holds a Master's in Pharmaceutical Medicine from Hibernia College. He was a medical advisor at Lethico Pharmaceuticals Limited, Indore, and head of operations at Pfizer India.
There is some delay in her flight, so we are going to start from the second speaker, Narahari Shastri. Dr. Narahari Shastri, I would like to invite Dr. Narahari Shastri. Just a small introduction by Dr. Sangamwal.
Sorry. Now, Dr. G. Narahari Shastri is currently the director of CSIR, Northeast Institute of Science and Technology, Jorat, Assam. Prior to joining the director, he headed the molecular modeling division at CSR, Indian Institute of Chemical Technology in Hyderabad. He completed his first postdoc from Hebrew University with Professor Sassan Sheikh, and subsequently second postdoc from University of Freiburg, Switzerland with Professor Thomas Bailey. He is a recipient of several awards, which includes J.C. Bose National Fellowship of the Department of Science and Technology, New Delhi. He published more than 300 research papers in reputed journals. With these great accomplishments in his life, I invite Dr. Shastri for a talk.
Caller mic. Thank you very much. At the outset, I would like to thank the organizers for giving me an opportunity to come here. I have been visiting NIPER from 1999 onwards, and it's a pleasure to be here. Can I have my slides? So today, my lecture will be slightly different from the lots of intense clinical data that you have been hearing from the morning. So I just wanted to look at the different perceptions that we have on our understanding of disease, health, and drugs. While the pharmaceutical chemistry, pharmacology, pharmacognosy, pharmaceutics have played a very important role, there is a separate vertical which separates it from medicine as well as the natural sciences, chemistry and biology. I just wanted to see from chemistry, it's just doing experiments, creating your own molecules. And if you look at biology, this is like observing. So they are quite different, and chemistry is sort of associated with diversity, whereas biology is associated with complexity. But how about biochemistry? Biochemistry is slightly different, but what is more different is chemical biology, doing biology with chemistry. While we have been getting divided into these perfusious slots that are there, we are very happy to see that all of them are coming together now and then talking to each other. So this is probably possible with the drug discovery or biology or mathematics. So 1950s, if you look at probably the drug discovery is associated with pharmacists, pharmacologists, and probably chemists have played an important role, and biologists have entered, and now computer scientists also have entered in the area of drug discovery. So earlier we have logic, representation, reasoning, these things have played a very important role, and now probabilistic modeling, learning, computations are also playing a very, very important role in the drug discovery. So when you look at the transition, we are going from the conventional mathematical models to probably artificial intelligence and machine learning. I will try to go through it. There are different scales. You have physiology, there are clinical parameters, there is biophysics, and also physical chemistry, and when you go to the bottom, you have quantum mechanics. So for example, there is a theory called there is a drug receptor interaction. There is a small molecule with bind with the
known receptor or unknown receptor or somewhere and elicits a biological response. So the host allows only a specific guess into it, just like the lock and key model. So this molecular recognition and specificity appear to be very important, and this particular model was there close to a century. And we are also having a thought process that there is a disease which has one target and one drug. Now we know that this is probably not a very acceptable idea. So we also have receptors are usually related to proteins, and to predict the three-dimensional structure of a protein from the amino acid sequence, or how does a protein fold into the structure, is a very, very interesting question in its own right. So nature does this protein folding. Can we understand this act of Mother Nature, or how a three-dimensional structure comes from the primary sequence? So there are several questions that are there, which led to different fields like computational biology, bioinformatics, chemoinformatics, molecular modeling, so on and so forth. So when you look at a very quantitative way of understanding, this is more than 2 centuries old statement, that when you can measure what you are speaking about it and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely advanced to the stage of science. So this is something. Can we subject biology to mathematics, or medicine to mathematics, or what we are talking about, this thrombosis or ischemic stroke versus cardiovascular complications, and all of them, is it possible to subject to mathematics? That's the question. So as somebody like me who started with computational quantum chemistry, you can subject everything to mathematics, provided it has 2 particles. And if you have a third particle, you cannot solve it, and there are so many approximate ways of solving it. And we learned how to subject various problems in natural science to mathematics very effectively, and this particular area has emerged into something very, very strong in chemistry, material science, biomaterials, and so on and so forth. So if you look at drug discovery, there is a new therapeutic indication, and from there you can try to develop a drug, or there is a disease, then you can try to develop a drug for the disease, and what you have to do is whether you can measure the risk versus benefit ratio, because every drug will have a sort of a side effect and also might have some therapeutic potential. And you can try to look from the structure of a molecule, or several molecules will elicit a particular biological response. So there are different ways of discovering drugs based on a drug approach, drug-oriented approach, or a disease-oriented approach, or a structure-based approach, or a ligand-based approach. So we have come up with different protocols of looking at drugs, and essentially you have to look at the drug discovery and drug development, which are different ball games. And in the drug development, things are getting more and more complicated due to the several factors that are there. And drug discovery, also there are more and more advances that are there. So identification of new chemical entities is one, and drug repurposing is another area which has emerged very strongly. And we are also looking at the formulations. The phytopharmaceuticals or botanicals have played a very important role. And in India, we are also trying to look at the Ayush mode, where people are looking at the herbals and other drugs. So let us look at some simple things. I don't want to talk very complicated things today in the morning. We try to say that why are molecular structures important? Because people try to look at the structure determination. The reason is physical, chemical, as well as the biological properties are determined by the molecular structure. This is a concept that we all know. So then we extrapolate it and then say that similar molecules are expected to have similar properties. Is that true? I like this paper, which appeared 2 decades before, that you have 8 similar molecules and we are looking at some different properties, like volumes and surface potentials. They have a particular pattern. Hydrophobic and polar regions, they have a particular another pattern, and you have hydrogen bonding donating potential, yet another pattern, hydrogen bonding accepting potential, yet another pattern, molecular electrostatic potential, we have a different pattern. So the type of similarities or differences that you look at depends on the question that you pose. So it becomes more and more complicated to subject it to mathematics. So if you look at the molecular structure representation, we know the geometric structure, but we also have to look at the electronic structure, electrostatic potential, connectivity. So you have a one-dimensional structure, two-dimensional, three-dimensional, four-dimensional, five-dimensional, and higher dimensional structures. So there are different ways of looking at these molecules based on different parameters. Probably the computer will be very happy if you give it in a bit vector. So how do you transform the knowledge that you have into a form of a bit vector, which is very, very possible now, and lots of people are working on it. So chemoinformatics has become very important. So we all know that the SMILES format or INCHI key, for most of the students that they will be knowing it. So subjecting a complex biological information to mathematics has made a lot of inroads, and there is a problem with this information and simplicity. If you want to simplify it, the information will be lost, and if you want to get more information, you will have to go to more complex things. Even if at a fundamental level, you can see that reality can only be measured to the limit derived by Heisenberg. Heisenberg's uncertainty principle, all of you probably have heard at some point. It says that you cannot measure the position and the velocity or momentum of any particle with infinite precision. The very process of measuring will perturb the system when the system is very, very small. So we attempt to model the reality of an analog world with digital computers. Hence our models, however accurate, will only be depicting the epistemological reality but not the ontological reality. In other words, our models, however honest, will always be approximate. Having said that, the innate motivation of any models has been to mimic the objective reality as closely as it can be perceived. We all know that computational models and theoretical models have some approximations, but experimental models have higher levels of approximations. The error bar, every measurement that you have will have an error bar. There was a theoretical chemist who had taken 190 different examples where the experiments are not in agreement with the computed results. And they have challenged that these experiments are not correct because they are not in agreement. The reason is these experiments were done with a type of analytical instrumentation which is not accurate enough. So we will have to have a very good interplay between theory, experiment, computation to get the correct results. So nowadays in chemistry, when I did PhD about 3 decades before, all the chemists used to be in some isolated place and they never used to talk to experimentalists, and the experimentalists will never bother about the theoreticians. But now you will have a very good interplay between theoreticians and experiments. So is in biology. So about 3 decades back, people in pharmacy colleges, they were not doing high-level research. Most of them are having a different thing. But now, very, very high-quality research is being done in pharmacy colleges. So we have to somehow circumvent this mindset that this is a particular area and we cannot do it. We can do any area, and we have lots of data, and I'm so happy to see the morning lectures that we have a huge amount of data and analysis by the clinicians, whether it is a transcriptomics or protein structure comparison or binding energies or the binding scores or ligand similarity and data mining and network analysis. There is a lot of data that is there, and computer-aided drug discovery market appear to be very strong. I will go through it quickly because I just wanted to tell you that even in pandemic, the artificial intelligence and machine learning has played a very, very important role. Let me try to look at the field that artificial intelligence is indispensable in 21st century in any field. I will try to come back to this. But more importantly, I wanted to address a particular problem, especially in the context of India. Most of us who are doing computations, like we are looking at supercomputing, high performance computing, the capacity, capability, mathematical modeling, statistics, first principles calculations and simulations. And we also know about software, database, web portals, apps, and IoT-based device development. However, the computational models can be divided as people who develop theory or people who develop methods based on the theory, the methodologies to solve a particular problem. And then there are people who develop algorithms and programs and softwares. And these particular people can be for developing them from academic purpose or commercial purposes. And there are application scientists who try to effectively utilize these softwares, and there are users, and the users are very high in our country. And probably this theory about 30, 40 years before, we used to have a large number of people, but somehow the algorithms and program and software developers, that number is getting down. Very, very small number is there compared to the size of the country. When the users are more, if they have no idea about the methods, algorithms and theory, they are sort of becoming addicted to using them because they use it in a black box program. So I just wanted to say that some of these computational softwares are very expensive. And we try to overtly depend on the commercial software in academic training leads to some undesirable long-term challenges. The reason is lack of availability of this software for commercially deprived academic institutions. For example, a small college may not be able to afford it. But more importantly, are people who are reluctant or averse to use commercial software in principle. I may have money, but I don't want to use a commercial software because that will not allow my students to develop their knowledge. And it may be too expensive, especially in the third world countries. It may be most important, it's a black box, and often the methods and algorithms are not clear to the application scientists. This is not good. And from a very practical point of view, you may want to make an incremental change to the software, right? So when source code is not available, when you use it as a black box, it's difficult to incorporate even small incremental changes or new ideas with the existing software. So this is what we feel. When the source code and everything is available, you know what is the method and then you may be using it. But if you have a new idea, you can implement it by writing a small script. So the way forward is strengthen human resource across the country in the area of computational modeling. It is important to inculcate the culture of writing our own codes and share it across the academic community. This open source culture has to be developed. And many people, Debashish Mohanty also has developed several codes, and our group is also doing. There are Bharatam Prasad, his group has developed quite a few codes. And while there is a lot of scope in developing commercial programs, they may be restricted to profit-making institutes and not for pure academic setup. So we try to develop a code called Molecular Property Diagnostic Suite and developing this indigenous open source drug discovery software so as to de-addict the academic fraternity. So this is very easy to say but difficult to implement. And we started this idea I got in 2004, and we started working in 2011. And some of this, one paper was published after a long time, and here you can see Bharatam Prasad also is here. And this particular idea of developing a molecular property diagnostic suite, which is an indigenous software tool, which is disease specific, has been developed, and we are continuously working on it. It may take some more time because these things will take a lot of time. The molecular property diagnostic suite is being developed with the purpose of strengthening computational drug discovery in the country. We have different modules like data library, data processing, data analysis, and advanced modules. We have published that first with tuberculosis and diabetes in 2017, and the general theory was also published. This year we published a fragment library module, and these things are under preparation. I just wanted to tell you that this molecular property diagnostic suite will integrate all the data and tools that are there in the open source, and we also write several of our own codes. And with Galaxy,